Hey, Eli.
Hey, how's it going?
Good. You?
Going pretty good, actually. Josh might be joining us for a bit of this meeting today.
Oh, terrific. Has he got the link? Hi, Tyler.
Uh, Probably just gonna actually come and sit in the room because we live together
Oh,
now.
oh,
So
okay. Yeah,
yeah,
that's great. Yeah, I can
How's it
see
going?
if he wants, but yeah, yeah. Missed you lately, Tyler. Hey, Josh. How you doing?
Good, how are you? Yeah, I figure I'll just hop in a second and sit in Eli's chair.
Yeah, you're certainly welcome to join us.
I have been better, that's for sure.
Oh, really? You've been sick or busy or what's?
Yeah, I've been sick last
Oh,
month
I'm sorry to hear that.
or so. Yeah, been not feeling so hot. So I
Oh,
figured I was finally able to get on a computer today and started
yeah.
answering it. So I've got like a month's worth of emails and stuff I was looking up. I was like,
Oh,
I'm already on here. I might as well see if I can hang out or if I can
Yeah,
survive for the
yeah.
next couple hours.
Yeah, okay. Well, yeah, it'll be a little more qualitative than mathematical. Well, I'm going to describe the mathematics basically. Hey, Kevin, how you doing?
Doing just fine. How are you guys?
I'm good. Let's see. Yeah, couple more here. Let's give them a few minutes.
If I bow out an hour and it's not because of the lecture, it's because I'm
Okay.
dying.
No, I'm going to get this all online. The version of the book that's online now is good through chapter 14, through the standard model. So everything I covered up to that, what I'm talking about last week and this week, and it will be string theory, a very light introduction. No, light's the wrong word. Very basic introduction to some string theory. I want you to see that there's actually a straightforward canonical quantization that leads to a really rather surprising result. And we can get to that at least descriptively. I was a bit optimistic thinking that I could get through this in 2 weeks and write it all up. As a postdoc, it took me 5 weeks. So it's just a longer calculation than that. But you can find details in the book by Green, Schwartz, and Witten, Superstring Theory, and there are numerous other books now. Yeah, I had a nice list. In fact, let me find that list. What happened here? There we go. My screen suddenly went wonky. But I think I can find these references for you. If I can just, I got an out of the blue email from someone in Turkey who wanted to know all about, initially black holes, but eventually string theory and you name it. And I was able to send them a bunch of references.
that's cool.
Yeah. Yeah. Oh, that's weird. What is the problem here? Oh, I see. I'm spelling it wrong. Emery. And yeah, I had this list. Yeah, okay. So Green, Schwartz, and Witten is a standard one. That came out in about 84, the mid 80s, and really lays out all the basics that were known at that time. But then there's a good book by Polchinski called String Theory, Volumes 1 and 2. Then Svebak, A First Course in String Theory. And I've also come up with a couple of sets of lectures just by Googling on, string theory. There are some nice elementary presentations. So let's now, Eli, Kevin, where did we leave off last week? We probably got the string equation of motion. I think we wrote the action. I was hoping it would still be on the board here, but it's not. Let's just review a bit of it. The Nambu Goto action is a straightforward calculation of the area of a two-dimensional surface. So the picture you should have in space-time, whatever dimension of space-time, is a string-like thing sweeping out a two-dimensional surface, parameterized by some variable sigma that we can take to run from 0 to pi, or sometimes we'll see 0 to 2 pi. And then tau is a time-like coordinate as it moves and sweeps out a world sheet. And if you write the, and this will be the Nambu-Goto action, from pi alpha prime, then you have minus x dot squared, let's see, times x prime squared minus x dot x prime. I'll tell you what this all is. This x is a position vector in some n-dimensional space-time, n-1 spatial dimensions. And it's a function of both sigma and tau. So for a particle, we had a position vector x mu of tau that described its world line. And now we have another parameter that describes the string. And this gives the plus here. It's minus on the bigger term because x dot is a time-like vector. So so this will be positive. So this works out sensibly. The minus sign here gives you a positive sign on your momentum and your Hamiltonian. The alpha prime constant here, this constant is just half the tension in the string. If you work out a classical version of what this all is and make it relativistic, there is tension in the string because it may be spinning end for end, or if it's a closed string, it can be spinning around, say, the axis of a circle. You can picture that produces tension in the string. Either way, that physical parameter has units. If I think you divide by h bar c, you find it has units of, let me think now, is it inverse length squared? And so this alpha has units of length, and you can define a unit of length that's typically taken to be the square root of twice alpha prime. Alpha prime is called the slope parameter because it comes up in a later calculation as a slope, right? Now, there's a simpler form of the action, and I go through, I will post these notes. Let's see. I've got to get Davis get his thesis out, after this class. So I'll get back to this as soon as I can, but I will get notes on all this posted. What you do is you look at a two-dimensional metric, Hij, on this, and it turns out to be the d x alpha d sigma I. If you let sigma I be tau and sigma, then contract those a pair of those tangent vectors, you get a metric. And we showed last time that when you rewrite this in terms of that metric, you get what's called the Polyakov form of the action. which isn't due to Polyakov at all. Let me pull up my notes here so I can remind myself of a few of these details. The Polyakov form, which all you have to do is, let's see, minus 1 over 2 pi alpha prime. It turns out you get a factor of 2. But the volume element in space-time goes like the determinant of the metric. And we have a metric, so we can just write the determinant of this metric and then times 1. Well, 1 is going to be basically h contracted on this. We'll give a factor of 2. That's what gives this. So if we write something like this, alpha d sigma I d sigma j, this factor is just h squared is 2. So let's see, is that where that 2 comes from? In any case, let's see, what is it? Yeah, 1/2 of that. Yeah, so we define the Polyakov action to be this times the area, and then this this factor gives another factor of 2, so you end up with 4 here. So this becomes the Polyakov action. Yeah, the Polyakov action was actually written down by Deser and Zumino, probably a decade before Polyakov showed that you can really use it very effectively in quantizing the system. So Polyakov is named after Polyakov because he used it, not because he was the first to write it. Now, if you vary either of these actions, you get a set of field equations. It's if you look at this looks like n scalar fields in 2 dimensions, and that tells you what you really have here is one way of looking at what you have is that it's a scalar field, a massless scalar field in 2 dimensions with conformal invariance, right? Because the way this transforms, okay, this transforms inversely with sigma, so this will go with sigma, and that will balance out these two. So it's scale invariant. You can rescale sigma I any way at all, and it leaves this whole thing invariant. And I showed, all right, if we take an h tilde to be proportional to h like this, you can diagonalize any 2-dimensional metric by a conformal transformation. You can choose phi, and this will be in the notes. I showed it last time. It'll be in last week's lecture. You can find a phi that will make, and a set of coordinates in 2 dimensions that will make this h just be the 2-dimensional Minkowski metric. So that gives a lot of simplification. You simply get a wave equation for x, well, let's see how I want to write it. Well, sigma I d sigma j, hij, where this is just eta. So this becomes your field equation. With the Polyakov action, you treat h and x as independent, and when you vary the metric in a theory like this, you get the stress energy tensor. I like to call it the energy tensor because nobody works with stresses anymore. Some people will call it the energy momentum tensor. It's that too. But the energy tensor is what you get when you vary this action with respect to h. And because we treat h as an independent variable, the energy tensor Tij will be 0 as an additional condition. In order to solve that equation, you just write Fourier modes. And did we write this down last time? Kevin, do you remember how far we got with the solution on this? Oh, I'm not.
The last things I wrote down were more just descriptors of what we were talking through. I
Okay.
was more listening, I think, toward the end of that.
Yeah, that's fine. Yeah, the details, and you may want to look into the details because string theory has been with us for 50 years, and there's a whole lot. We are absolutely just scratching the surface here. But
Yeah, last thing we were talking about that I was writing down was conformal symmetries and things.
yeah, okay. This has a lot of symmetry. Talk about this. So we have conformal invariance of the 2 metric. We also have global Lorentz invariant of this guy. This turns out to be really important. And then we can translate. So Poincare, global Poincare invariance on the space-time indices. The space-time that all this happens in is called the target space. And so you aim your string into this bigger space. But these are continuous symmetries. And Another's theorem gives us corresponding conserved quantities. And already, we've talked about this before, what those conserved quantities are. They're the energy, if you have a conserved energy, Hamiltonian and momentum, total energy and momentum of the string. And you have a conserved angular momentum, total angular momentum of the string is conserved. Now, what that means is that within the structure of the string, we have Poincare symmetry. The magic of string theory happens when we quantize it and find that the quantum theory still allows us to build this symmetry. We know that symmetry underlies general relativity. Local Lorentz invariance gives us general relativity. Okay, so I keep catching my foot on this treadmill. Okay, so we have a simple wave equation, and we can write a general solution to it. So let's do. So x alpha, we can write as some initial position and some momentum. So, all right, velocity times time. So I'm going to put an initial v times time, but eventually I'm going to replace this 1 over m now in fundamental units, multiplying by h bar and c, however we need to. A mass is an inverse length. So this factor goes like the length. P goes like 1 over a length. And we want this to be a length. So let me see. We end up writing this as a length squared. Why is that? And how dimensional? Let's see. Anyway, we write the 1 over m as a length squared. And then we have a series which I'm going to write as I L over 2. L is a length parameter to make a length. Then we have a sum over modes. Over, well, everything but m equals 0. The 0 mode is the momentum. So we have m not equal to 0, but m's going to run otherwise from minus infinity to infinity. And we'll have modes e to the I m sigma and alpha tilde, let me call it. These are independent, alpha and alpha tilde. E to the minus I m sigma with an e to the minus I m tau. And reality, if you just require that this be equal to its complex conjugate, this is all real. But what you find is that the conjugate of these guys has to be alpha of minus m. There's a Lorentz index on each of these. And the same for the tilted ones. Mu m conjugate is alpha. Like that. So that condition guarantees that that x is a real position vector. A great deal of what's done in string theory is done in light cone coordinates, and you'll know from just classical mechanics, we probably did a string in classical mechanics. If I define u to be tau plus sigma and v to be tau minus sigma, then the wave equation, this sort of wave equation, this is minus x mu double dot plus x mu double prime equals 0. But it diagonalizes this. So the equation simply becomes dx alpha du dv equals 0. So in the light cone, we can write this as a function x right of a right moving mode that will depend only on v, and a left moving mode that will only depend on u. So you can always decompose the string this way. One of the remarkable things that happens in string theory is that these right and left modes become completely independent of one another. You get two completely independent wave motions. So this happens in the closed string. So if you have a loop of string, you have right moving modes around the string, modes of oscillation. Remember, it's under tension, so then it can vibrate transversely. And you have left moving modes that are independent. Have any of you heard of the heterotic string? All right, the heterotic string treats the left and right moving modes differently. The left move, doesn't matter which one. One of the modes is basically bosonic string theory. The other mode is a superstring and lives in 10 dimensions. That's weird, okay? Mathematically, it's totally consistent, but I have a hard time thinking about what it means for the right moving modes to think they're supersymmetric in 10 dimensions and the left moving modes to think they're bosonic fields in 26. It's been conjectured, and I don't know whether it's been proved, that the 10-dimensional supersymmetric models are compactifications of the 26-dimensional bosonic string. And in that case, it makes a great deal of sense because they're both really living in 26 dimensions. We're going to get to why it's 26 and hopefully today. But the but part of the space can be compactified from the point of view of the say left moving modes. We're not going to do the heterotic string today, but that's what it is. So the energy constraint. Now I've got a nice calculation here where I actually do the coordinate transformation. But this vanishing energy, and this looks like the electromagnetic energy tensor. This looks like the x alpha d sigma I d x alpha d sigma j minus 1/2 hij. Oops. Well, actually, eta ij is right. With the contraction eta kl dx alpha dx alpha d sigma k d sigma l. Can you see that there? That's the usual form. You write the same thing for electromagnetism, for the energy momentum tensor. This is symmetric, so there are only 3 components. And because we're in 2 dimensions, if I take the trace of this, the trace of the metric here gives 2, and half of 2 is 1, so these 2 terms cancel. So this is traceless, so it only has 2 degrees of freedom. And in light cone coordinates, let's call it MN for light cone, it's diagonal. We get a T++ and a T minus here for U, or UU and VV if you like, and off diagonal is 0. And give us an exercise to show that that's actually still traceless. It is, but you have to think about what the metric is. Okay, so moving along, we're doing what we would do with like any theory, right? Beginning of, I don't know, ages ago, winter semester, I guess, we did canonical quantization. We can do that here. So what we can do is, well, continue with our solution here. We need to impose boundary conditions. So we can have closed string or open string, and those have slightly different conditions on them. For closed string, you have to have, let me just write the condition here. You have to have x alpha at sigma plus pi and all tau equal to x alpha at sigma tau. Just a periodicity condition on the string, and that means you only get even modes. You get a 2 in these exponents. So so you get either 2i and sigma and so on from that case. Even modes in this expansion. Most of the rest of it is the same. For the open string, you can use either Neumann or Dirichlet boundary conditions. And if you use Dirichlet boundary conditions, it has a very, very early consequence that no momentum flows off the ends of the string. You set the spatial derivative, the tangent vector to the string, our string's gone, but dx d sigma is tangent to the string. And if you set that to 0 at the ends, then you find from the energy condition that no momentum can flow off the end of the string. It also means anywhere along the string that you have no you have no tangential oscillation. That the vibration of the string is totally transverse, and we know that's nice for field theories. It doesn't help for quantization, but that yields to technique. Okay, so we get a solution for the open and closed strings. In the notes, I work out both Dirichlet and Neumann boundary conditions. You can do either one and find a consistent set of solutions for the string. People usually use the Neumann boundary condition. Okay, let me just write out the. So I'm gonna turn this into closed string, because all I have to do is put 2's up here and here. So otherwise, I'm pretty sure everything stays just the same. Let me look at my, yeah, then we write this coefficient as L squared. And let's see. Well, that works out. I won't try to think through the units just now. And we can write a similar expansion for open string. Now, the next thing we do, okay, so canonical quantization, what do we do? We do the Hamiltonian formulation here. So the next thing is to find the conjugate momentum and find the Hamiltonian. Well, the conjugate momentum, think for most of this discussion, I'm going to stick with the original sigma and tau coordinates. Let's see, so there's the boundary condition for closed. We've got the closed string solution up here. We can write those energy conditions if we'd like. Yeah, the Hamiltonian, right, to find the conjugate momentum, it's going to be the variation of the Polyakov action with respect to the velocities. And it turns out that that's just 1 over 2 pi alpha prime. Sorry if you're using different times x alpha dot. So the momentum is just proportional to the velocity. Simple free field theory, not too surprising that we see that. And then we substitute that to find the Hamiltonian. Okay, so what do? We integrate over the length of the string, the momentum with the velocities minus the Lagrange density. And there's no surprise here. We're going to get a half x dot squared plus x prime squared, where what I mean by x dot squared is the x alpha d tau the x alpha d tau. That's just x dot, and when I use squared or a dot product, I'm going to mean that target space dot inner product with the Lorentz metric. Okay, so the Hamiltonian, has 4 pi alpha prime here, which is what? That's L squared over 2. I mean, you can go back and forth between these units. This is twice alpha prime. So then what? We also have the energy constraints, and those turn out to be, right, if you work through it, this gives you 2 conditions. You get x dot dotted with x prime equals 0, and you get the sum of squares. 1/2 x dot squared plus x prime squared equals 0. Okay, so we got more than an average number of conditions here, but these, okay, they're harder to think than, they're harder to show than you think, because there are factors of 2 and L squared and alpha prime all over the place. But they're not really that bad. They're not really that complicated. They come out in a straightforward way, like you were working with a parameterized particle. Okay, this condition is what I was telling you. Okay, the component of the momentum, remember, x dot is our momentum, essentially. So the component of momentum tangent to the string is 0. That tells you there's no stretching and contraction of the string. And it also tells you that no momentum is flowing off the ends of the string, which is all a good thing. This condition, that's the Hamiltonian, right? That's what we just got for the Hamiltonian up to some constant. Why is the Hamiltonian 0? The answer is straightforward. It's because the system is relativistic, right? If you had a non-zero Hamiltonian in space-time, it's a preferred energy. And that would give you a preferred time, and you don't have such things in special or general relativity. So what usually comes of that is that a relativistic Hamiltonian will vanish. And that doesn't cause any particular problems. In fact, it gives a very interesting condition, which I was mucking with a great deal today because I got everything to work out just right, and then except for factors of 2. And I've spent like days looking for factors of 2. I think I've found where most factors of 2 are now, maybe all the factors of 2. In any case, we can write the Hamiltonian for closed string, and maybe I'll limit my talk today to closed string. Yeah, you can do the open string as an exercise. How's that? All right, the Hamiltonian. When you substitute in the mode expansion, the Hamiltonian is the sum, m equals minus infinity to infinity of alpha m, let me use mu, alpha m minus m mu. So m and minus m plus the other pair minus m, where notice that I've included n equals 0 here, but there is no n equals 0 in this expansion. Basically, this is n equals 0. So where the alpha 0 mu is, I believe, is L over 2p 0 mu. And since, let's see, okay, the 0 mode also, notice we're summing here. And if I sum this alpha 0 mu, that's L squared over 4 p0 mu, p0 mu. That's just the mass squared. So this turns out to be an important relationship. This tells us that the mass squared, if we work out the details here, it ends up being, this L squared is twice alpha prime, and I believe this ends up being alpha prime over 2 times this sum, m not equal to 0 of the alphas. Okay, like this. So that tells us that the mass of the string is related to the mode of oscillation. This is one reason that a string can represent all the fundamental particles, because if that string vibrates with a different combination of modes of oscillation, it has a different mass, looks like a different particle. Well, we have a doubly countably infinite number of these modes, so we can describe quite a lot of particles with a single kind of string. The goal here is to describe the standard model and gravity with a single interaction, right? A single interaction that occurs with string. And I'm not going to go into the details about how you write the interaction terms for string, but basically one string can break into 2, or 2 can combine into 1. One thing that means is that an open string can join and become a closed string. So open string theory necessarily includes closed strings. That's an interesting observation in itself, because it's the closed strings that carry gravitational information, among other fields. But gravity is through the exchange of closed strings. So let's see if we can get to where some magic happens. Yeah, what do we do next? We're doing the Hamiltonian formulation. Working through this, it's going to look familiar to what we did in field theory when we worked through all those Poisson brackets for the various fields. And so we start with canonical brackets. x alpha of at equal time brackets. So just need a sigma here, x beta at sigma prime, right? Those are positions, that's 0. And we also get 0 for the momenta. So pi alpha of sigma with pi beta of sigma prime also gives 0. The non-trivial one is when you have one of each, sigma and pi beta of sigma prime. And what you want here is, well, essentially 1, when these are the same index, well, you need the Lorentz metric there to give that. And then you need a delta function in sigma, sigma prime, like that. So these are then the canonical commutation relations. And you remember going through lengthy calculations to show how those canonical commutation relations for position and momentum, canonically conjugate momentum, turn into Poisson brackets on the mode amplitudes. You get one between x and p, and you get various commutation, not commutation relations yet, Poisson brackets between the various alphas. And as I say, I'll post this calculation in a bit. It's still missing some factors of 2 that I'd like to sort out. But ultimately, I'm scrolling down my notes here. Ultimately, we get them. Yeah, here we go. I'm trying to find where I've written these down. Okay, here's one. Now,
A quick question on that before you move on.
Yeah.
Does the factor of the metric there, does that cause the same problems as it did back in, oh geez, I'm trying to remember. Was it the electromagnetic where we had the positive and negative states?
Yes, it does. And you handle it pretty much the same way. What we're going to do ultimately, not today, is to put constraints on the space of states. So certain operators will, we remove, let me say it again, what did we do? The second time we did it, right? We went ahead, added a term that broke the U1 symmetry for electromagnetism. That meant we kept all 4 modes of the vector potential, and each of those had a conjugate momentum. We quantized that, and then showed that the resulting theory had both positive and negative norm states, so it's not a Hilbert space. But we found a condition we could look at a subclass of states that are annihilated by a certain simple operator, the raising operator, the lowering operator, I forget what it was. Look back in the notes, you'll see. And it's very much the same thing we do here. You choose a condition that your space of physical states are those states annihilated by a certain operator. And you find that that eliminates the negative norm states. Then you show that the 0 norm states form equivalence classes. And so the equivalence classes themselves form a positive norm Hilbert space. So that will be the procedure here too. That gets around that difficulty. What else can I say about that? Nothing yet. I'm worried that I've left off one. These are unknown mode amplitudes. I can pull a factor out of them, and it's convenient to pull a 1 over m out of that factor. And for that reason, in fact, when you calculate the Poisson bracket for these mode amplitudes, you find that they all vanish except for alpha mu with, let me be sure I'm writing this correctly. I backed up too far in my notes here, sorry. Let me just find this. Yeah, almost. I had to work out a representation for the delta function. That wasn't working very well. Ah, here we go. So, yeah, so for minus m here, you get I m beta mu. So we do have this sign problem, but we know how to handle it. Or if you put one of these down, actually, you can write that as a Kronecker. I'm not sure that actually helps with the issue you're asking about, but if you put in these, all the rest vanishing except for x and p for x alpha and the zero modes, beta, you're going to have delta alpha beta here. So as you would expect, the center of mass, these describe the center of mass motion, right? This is just x plus vt. And the center of mass motion, I mean, you could shrink the string down to its center of mass and it should be a particle. And, so it is particle at position x and momentum p moving in a straight line. That's the solution to the equation of motion. So, that all makes sense. And those do satisfy canonical commutation relations. Okay, so aside from a factor on my delta function, I'm getting that to work out. Then, yeah, all the other ones vanish. So then, the next thing we want to do, we have the bracket. So we can quantize this. We can put hats on everything, multiply by IH bar, and change brackets to commutators. So we're good when it comes to quantization. We may need some tricks to form the Hilbert space, but that's okay. The other thing we want to look at are the conserved quantities due to the Lorentz transformations. And these are just what you would think. You have conservation of total angular momentum. So let's see. Here. The total angular momentum is the integral over the string of all of the momenta, and that's a conserved quantity. If you just apply Nether's theorem, right? And it's simple here. You don't have to do a lot of variations and things. What you can do, so at any 2 times that vanishes. Okay, so you take the action, you do a variation of the action, vary everything in sight, and now you let the variation be the symmetry, the variation of the coordinates under the symmetry only. So you're restricting the variation. That means that the variation of the action vanishes identically. So now you integrate by parts and get the field equation, but you keep the surface term. You don't assume that you're holding the boundary fixed or anything. You keep that surface term. And now you impose the equation of motion. So that surface term is all that's left. And that surface term is telling you that you have a conserved current. It's basically the vanishing of the divergence of some expression that depends on your symmetry variation. And it turns out to be this for the translational symmetry. For an infinitesimal Lorentz transformation, right, that's described by parameters that are antisymmetric when doubly covariant. When you raise an index, the time ones become symmetric, and that gives you the boost. And we went through this in the early chapters of the field theory book, so you can look back and see how that works. And I've worked it out in some detail here, and this works nicely. What you find is a second conserved quantity M, you knew this time. When you pull off these constants of the transformation, you find you have M you knew equal to, again, it's an integral over the string pi, but now it's x mu pi nu minus, guess what? X mu pi mu. So very much the thing that you might just write down mindlessly and get it right, despite the difficulty of getting all the functions of 2 right if you actually do it carefully. So that is the angular momentum of the string. Now, this turns out to be really important. You work it out, you substitute in the expansion, and it turns out that M is given by, well, nothing you wouldn't expect. This ends up being a half, then you have x mu p nu. You have the center of mass, basically the orbital angular momentum, p mu 0. And then, let's see if you can see the bottom here, and I can actually write there. And I could be missing I wouldn't trust my 4s and 2s in this equation. There is an I here. And we have a sum with a 1 over m. And now it's a bunch of products of alphas and alpha m and alpha minus m. This sum is for m not equal to 0. Any of the expressions where you have a 1 over m here, you can't include the 0 mode there. You have to write it separately. But that's what this was. And then you have alpha m mu, alpha minus m nu, anti-symmetrized, alpha nu m, alpha mu minus m. And then and then the same with the tildes. Let me not write all that out, but the same expression, but put a tilde on each one. So it's each alpha and alpha tilde anti-symmetrized with itself at minus m. Okay, now the quantization of this involves a really tedious calculation, which I hope to eventually include, because I know you guys love tedious calculations, right? But I want to work it out. I like to see these things done right. So when you quantize, okay, these things become operators. This is a conserved charge of some sort. This is a conserved charge of some sort. I should give it a name. Maybe, what is this? This is P, except I've used P, so I won't give it a name. But this is the total momentum of the string. Actually, this one, I think this one does work out to be just P alpha. The total momentum of the string is the center of mass momentum. You quantize all this, right? You put hats on all the alphas. And now you compute commutation relations of everything in sight, right? You check your equations of motion. You want to define a space of states, and you do actually BRST quantization is the most common, which we haven't done. But essentially, it's a sort of a supersymmetrization. You're adding extra anti-commuting fields as a trick, and the equations of those anti-commuting fields automatically eliminates the extra terms you don't want. So it's a systematic way of implementing the kind of restricted space of states that we did for the electromagnetic field. I had hoped to give a presentation of the BRST quantization. I've got a nice paper that lays it out very, very simply. So maybe I'll be able to include that at some point in these notes, but they're not there yet, and I can't tell you more than that about it. Here's the magical thing that happens. We lost Josh right at the magic, too bad, but no magic. When you compute the commutation relations of these conservative charges, you get 0. Translations commute, it still looks like what you'd expect in the Poincare group. If you compute the commutator of these two conservative charges, now bearing in mind that we've already consistently quantized the string, right? We're talking about quantum string here. We're not talking about any particular interactions, but we're putting hats on these alphas. These things, notice, are constructed quadratically from the alphas. Okay. M of P gives the usual Poincare commutator for M and P. But the commutator of two of these M's doesn't always work right because you've got what are called central charges. And, I'm going to have to include this in the notes because I haven't worked this out yet myself. But let me see if I can write the answer. If you do it in light cone gauge, it's the commutator, you have an M plus and an M minus. It's the commutator of the M minuses that gets really hairy. It's a long calculation. I did this stuff, I mentioned I did this as a postdoc, that was 35 years ago, so I'm a little rusty on this, but you get the usual Lie algebra of the Lorentz group. All right, it's this sum and difference that's anti-symmetrized product of metrics and M's. Right, so the commutator of two M's is an eta M, anti-symmetrized on this pair and anti-symmetrized on that pair, which gives you 4 terms. You've seen that, we've worked that out in the notes. We've worked it out for spinors. The gamma matrices, that works. But in string theory, it turns out that when you quantize, there's this central charge, so that the commutation relations of these M's is not quite what you would expect. So if you have M mu nu and M alpha beta, so you've got a lot of generators here, what you generally get is beta mu alpha M beta, and then you have to anti-symmetrize mu nu and alpha beta. So you're going to have minus beta nu beta alpha minus beta mu alpha M mu beta plus, now if you switch them both, mu beta and mu alpha. That's the usual thing, but then there's an extra term. And let me just see if I can find it here. But the bottom line is that it depends on, hold on, I'm seeing it here, but now there's a term that comes out of the whole calculation, 1/12 M cubed minus L. You get a term like this, and that combines with another similar term, depending on the dimension. And if the dimension of the space-time is d, you get you get some constant here. And let's see, well, you get the number of spatial dimensions minus 24. So you have d minus 2 transverse modes of this oscillating string. And that, that will reduce to the usual Poincare algebra, in this case the Lorentz algebra, if you choose the dimension of the target space to be 26. And so bosonic string theory lives in 26 dimensions. And that, you know, at the time that came up, you know, it's a little funky, but it's still a gravity theory in 26 dimensions. And at the same time that people were first developing string theory, it was quite common practice to work with Kaluza-Klein models in which some of the dimensions are compactified. So you do a 6-dimensional theory and compactify 2 dimensions to get the 4-dimensional spacetime plus some spheres, say. And that's totally consistent with what we measure. The spheres are taken to be small enough that you don't see the oscillatory modes of the sphere. And now it looks just like a 4-dimensional theory. And the general thinking in string theory is that you do a similar thing here. And there are many compactifications that work. In order to get to 4 dimensions, you need to compactify 22. Okay, so choose a 22 sphere, or, you know, that one turns out not to be stable. But the problem is simplified some when you go to the supersymmetric string theories, of which there are a couple. One has an internal symmetry of SO32, one has an internal symmetry of E8 cross E8. And the supersymmetric strings have a critical dimension. This thing is called the critical dimension of 10. So you've used up a lot of the dimensions just to produce your supersymmetry. Now, a 10-dimensional space, you need to compactify only 6 dimensions. I think my first paper with Filial O and PGO Freund was a compactification of 6 dimensions. I forget exactly the space we compactified on. A fellow grad student of mine, Filial O, went on to look at further compactifications. And I think he found that if you have 2 spheres, 2 3-dimensional spheres, you can have a stable compactification of 6 dimensions. Do you guys know Laura Anderson? Did you overlap with her at all? She was here, what was it? It's a while ago now. Maybe didn't overlap, but she was a graduate student here. Or, well, she did a master's degree with me, then she went off to Oxford. She got a Rhodes Scholarship, went off to Oxford, and then did a postdoc at Penn. Anyway, she has a job now at Virginia Tech, and most of her graduate research and postgraduate research has been, she's faculty now, has been looking at compactifications in a systematic way. Turns out there are a lot of compact 6-dimensional manifolds. Now, if they have sufficiently nice properties, they might be Kähler manifolds. Kähler manifolds are spaces that, in addition to a metric, have a symplectic form and complex structure. And those 3 structures are related to one another in such a way that if you know 2, you can always find the 3rd. Those are called Kähler manifolds. And so if you have a Kähler manifold, which, you know, strings got a lot of symmetry, so you very well might, you can ask for compact Ricci flat 6-dimensional Kähler manifolds. Those are called Calabi-Yau spaces. And she's classified something on the order of millions of Calabi-Yau spaces, compact Calabi-Yau spaces, by looking at various properties that we want in the final 4-dimensional theory. And asking for compactifications on Calabi-Yau manifolds that respect that. You've all seen the picture of one, right? If you've ever Googled string theory, you see this marvelously twisted shape. You know that's a Calabi-Yau manifold. That's like a three-dimensional section of a higher dimensional Calabi-Yau manifold that somebody's figured out and made a cool picture. So the usefulness of string theory in the usual formulation hinges on a way of connecting it with the standard model, which we know works extremely well. And it has been shown that there exist compactifications with many of the right properties. For example, a paper in the middle to late 80s, Witten showed that there exists compactifications where proton decay is consistent with what we know. Now, let me back up and say this is a unified field theory. We have a large symmetry that because of this, because within the quantum theory of string, we have, these are operators, right? All these guys have hats on. So we're inside a quantum algebra. And inside that quantum algebra is the Poincare group. What that means is that this quantum theory, at low energy, written as a gauge theory, will contain general relativity. And it was shown in 1975 or 6 by Schwartz and Shirk that in fact that is exactly what you get. You look at the spin 2 modes, the massless spin 2 modes. So remember, we have a formula for mass, so we can find what massless modes look like. The closed strings have a massless spin 2 mode. And if you expand the string interactions and take a low energy approximation so you get an effective field theory at low energy, you find that it gives you the Einstein-Hilbert action as the low energy theory of gravity. The corrections to that low energy theory of gravity depend on that slope parameter, which is on the order of the Planck length squared. That L is something like the Planck length. So there are higher order terms in the curvature in string theory, but they are extremely strongly suppressed. All right, every factor of the curvature in your effective action. Right, curvature is 2 derivatives of the metric, so it has units of 1 over length. So you're going to multiply by length squared every time you go to cubic or quartic or whatever order in the curvature. So to go to quadratic order in string theory, the gravity theory, you get corrections that are of the order of the Planck length squared. So this very precisely is reproducing general relativity with corrections that we don't hope to measure anytime soon. The importance of this, I can't overstress. The fact that we have a quantum theory containing the Poincare, the algebra, tells us that we have a consistent way to quantize gravity. There's no question that the quantization of a piece of string moving in some dimension of space-time is a consistent theory. And so, there may be questions about how to formulate, how to write the quantum theory of various modes of the string, but it is a quantum gravity theory. There's a lot that's happened in string theory since these things. This was all known. Let's see, 20, 30 years, 35 years ago. What was added to it at that point in 1984 what happened that made people working in higher energy physics switch from doing supergravity theories, which had been shown to get around the Coleman-Mendeleev theorem. Okay, that's a no-go theorem that says since you can't in any ordinary way unify gravity and the standard model, they've got to be a direct product, so there's no unifying symmetry. But if you allow fermionic transformations as well, and you couple bosonic and fermionic fields by this symmetry called a supersymmetry, then you can. Then transformations between various fields can include the Poincare group non-trivially. And you can build a unified, what's called a supergravity theory up until 1984. The problem with those theories was that there were too many, right? You try to find uniqueness, and supersymmetry is a little tricky because you have to balance the number of fermionic and bosonic transformations. And what that means is in higher dimensions, right, the number of components of a spinner. Anybody remember how many components a spinner has? It's 2 to the half dimension, right? So in 4 dimensions, 2 to the 4 over 2 is 4, four component Dirac spinners. In 10 dimensions, it's 2 to the 5th, that you have 32 component spinners. You need a lot of bosonic fields to offset that. And, in 10, if you push it maybe to 12 dimensions, what people were actually doing was 11-dimensional supergravity, where the any higher dimension would have given you so many supersymmetries that you could construct bosonic fields of higher than spin 2. We've never seen a bosonic field of spin 3. And I know Desert, I mentioned Desert earlier, did a lot of work trying to show that such theories are not consistent. And they may not be. I don't think he accomplished a complete proof that they were inconsistent. And people have ways of finding ways around things anyway. But the supergravity theories suffered from not having a defined dimension, having some unique symmetry group. You could couple these things to very large internal symmetries. Well, supersymmetry limited that sum. If you add more than 8 supersymmetries, go up to 11 dimensions, it's more or less maximal without introducing more bosonic fields. And so something else beyond gravity could be there, right? But we haven't seen it. What happened in 1984 with string theory is that Green and Schwartz showed that the superstring admitted an SO32 internal symmetry. So in addition to the gravitational solutions, you had an internal symmetry group that was unique. Well, not quite unique, because when they brought this up the night before a meeting, Witten said, well, it could also be E8 cross E8. And that gives 2 superstring theories. But 2 is a lot better than saying, well, could it be SO27? Could it be an internal symmetry of SO93? Well, it could with a lot of models. So string theory was shown to have this unique internal symmetry and give you a form of supergravity. And so people who were doing supergravity switched over, started doing string theory, and pretty much have been ever since. To the point where if you ask a string theorist, what they're working on, they're not going to say string theory. Go ask Oscar, what he works on. He's working on the ADS-CFT correspondence, conjectural, known to hold in certain cases, where he relates a gravity solution to a solution in a conformal field theory. Well, this is a subfield of string theory. Yeah, if Alex were here, she could tell us about the 20 talks she heard at this conference last month. And every one of them is like some different area of string theory. It's a huge field. It's been around for 50 years now. And so, you know, you don't ask someone, you know, what they do in general relativity, you know, or if you ask someone, you know, does general relativity what they do, they're not going to say, oh, I find solutions to the Einstein equation. You know, they're going to say, well, we're looking at coupled spinning black holes. You know, Maria works on that, trying to understand the dynamics around black holes. Or we're working with what is this paradox between, yeah, okay, here's this cool paradox with gravity, might as well say. Okay, a black hole has a temperature, right? It's a certain associated entropy. And you can view that temperature as arising from pair production near the horizon, where a particle escapes and an antiparticle falls in, and because the black hole from infinity, that particle that falls in can seem to have a negative mass. Locally, it's just an ordinary positron, say, but as measured from infinity, it has a negative mass. And so the black hole has actually gotten lighter, and this electron has escaped off to infinity. Okay, that's fine. You know, Hawking is famous for finding Hawking radiation, and that's been theoretically verified a whole slew of different ways by different people. Very, very firmly established. But the paradox arises when you think of the necessary correlation between, in pair production, electron and positron form a correlated state, right? Epr paradox, all that stuff. So you know, you've got this electron flying off to infinity that is correlated with a positron that fell into a black hole. Well, also, that electron is part of a thermal state. Part of the proof of the existence of a temperature for a black hole is to show that the net radiation actually has a thermal distribution. In order for that electron to be part of a thermal distribution, it has to be somehow correlated with the rest of the thermal distribution. But a particle can't be correlated with two different things at once. It can't both be correlated with this thermal distribution and be correlated with this electron that's fallen into a black hole. And so the question is how to resolve that. And there are proposed solutions to that. Lots of publications and things. But if you ask someone, oh, you work in general relativity, what do you do? They're not going to say, oh, I'm looking for solutions to the Einstein equation. Nah, there are hundreds of those. And what people are doing is studying astrophysical objects, or trying to gain the kind of understanding of gravity that we have of, say, electromagnetism, right? I mean, general relativity is 100 years old, and then some. That theory's been around for a long time. It's mature. Well, string theory has been around for 50, and it's quite mature too. I suppose I should talk a little bit about other quantum theories of gravity, except there really aren't any. You've heard of loop quantum gravity. Okay, this is this is probably going to give some of the results that string theory gives for quantum gravity. Loop quantum gravity grew out of the effort to straightforwardly quantize general relativity. And as such, it is not a unified theory. It doesn't say anything about the other interactions, although you can couple them in various ways, and people have. But it's principally a theory of how to handle all the gauge degrees of freedom of general relativity, which is nonlinear and, as one of my committee used to say, very gaugey. All right, you've got the whole diffeomorphism group, right? This huge symmetry group for gravitating systems, and so you have to somehow control that. And so you have this large number of constraints that arise from all that gauge symmetry. And half of those constraints have been managed by what's called the, what is the name? Oh, it's the anti-self dual part of the spin connection. And you should remember the name of the guy who developed that. But that was back in the circa 1980, and that's the biggest step that has been made in the quantization of gravity directly. There's no reason to think that results in loop quantum gravity won't agree with quantum gravity results from string theory. In fact, there's been like one result from each. The group of string theorists came out with a prediction of the entropy of a black hole from string theory by counting modes of string. And it wasn't long before the loop quantum gravity people came up with a similar prediction from their version of quantization. But well, and the reason it's called loops, right? One way to form a gauge invariant thing is to, right, if you integrate the vector potential, well, that's a gauge dependent thing. But if you integrate it around a loop, now by Stokes' theorem, that's a surface integral of the field strength, and that's gauge invariant. So loop quantum gravity gets its name from doing loop integrals of this form and using those for your quantum variables. It's a way to try to control the gauginess of general relativity. I'm not sure exactly which variables they end up using at this point, but that's what loop quantum gravity is about. There's a bit of bitterness in that school because string theorists have gotten funded and loop quantum gravity people haven't. So you'll see some diatribes against, science is, misguided and all that kind of thing. I wouldn't pay too much attention, I mean, you choose to do what, choose wisely, because you're only going to be able to do so many projects in a lifetime. And so, pick good ones. But the thing that speaks to me about this is this right here. The fact that there exists a consistent quantum theory for something, well, string, but for something that contains a quantum operator version of the Poincare symmetry. That tells you have a quantum gravity theory, whatever else it predicts. It doesn't tell you that string theory is the only one, or that something sort of midway between, 4 dimensions and 10-dimensional string theory won't also prove to have that property. String theory requires 10 dimensions, but you might find some other models that have similar nice properties. I should say supersymmetry itself is a nice property. We're in danger of not finding it, but there may be ways around that, right, Eli? Yeah. But the supersymmetry makes quantization more convergent. We've seen when we quantize field theories that there are infinities, depending on the theory. And what happens in supersymmetry is you have this tight correlation between bosonic states and fermionic states. And that gives a cancellation of a whole lot of the Feynman diagrams. So things that would otherwise diverge actually cancel between the bosons and fermions, and you get a more convergent theory because of that. Supersymmetry, there are other things that are right about it. It actually unifies the idea of force and matter. Right? Fermions are what make up normal matter. Forces are now thought of as the exchange of bosonic fields, and supersymmetry constitutes a unification of force and matter in that sense. Another thing that strikes me about supersymmetry is that the field conjugate to gravity is a Rorita-Schwinger field, a spin 3/2 field. So you do a supersymmetry transformation. It couples the spin 2 mode, the graviton, to a spin 3 Haas particle that has a given field strength. Well, people have looked at Rorita Schwinger fields. Well, probably Rorita and Schwinger, but they find that it's not always consistent, that there's this certain auxiliary condition you need in order for it to make physical sense. Well, it turns out that in supergravity theories, the coupling to the graviton, it involves a symmetry. There's some gauge symmetry there. And if you can use that gauge symmetry of the supersymmetric transformations to impose that very condition, so that within a supersymmetric gravity theory, the Rorita Schwinger field is consistent automatically. So things like that make one think that, you know, supersymmetry is not a bad idea. You know, it's got some things going for it. It has some issues. It doubles the number of particles, and you have to break the supersymmetry by giving half those particles large masses to be consistent with what we see. Okay, yeah, maybe there's a way around that. You know, there are probably more questions than answers, but you know, I think if you are interested in doing high energy particle physics, theoretical high energy particle physics, you know, it's string theory that you want to be thinking about. You know, that's the best thing on hand, right? It may not be the final thing we come up with, but it's got consistency properties that go beyond anything else we've got in the way of a single interaction that demonstrably can give the standard model in gravity, making and breaking strings. I started this meandering talk talking about the proton. In a unified field theory, I think I showed this for SU5. You can embed the standard model, SU3 and SU2 and a commuting diagonal U1 symmetry into an SU5 matrix. The generators for SU5 can contain the generators for the standard model. But it also has 6 off-diagonal bits that don't fit in the SU3 cross SU2 cross U1. And those are called lepto quarks because they, I've written this before, so I'm hoping to call up some memories, but let's just write it. The generators are 5x5 matrices for SU5. And up here, you can put an SU3, and down here, you can put an SU2. And if you take a matrix 1, 1, 1, and does it need to be minus 3 halves, minus 3 halves? Let's see, that adds to minus 3 plus 3. So that's traceless, and this commutes with both of those. So those matrices give you SU3 cross SU2 cross U1, and then you have these so-called lepto quarks here. The way that these would act would be on 3 quarks and two leptons, but these particles here, when you write an interaction term in a covariant derivative of these fermions, you would find terms that are, say, an X particle acting on these leptons, and over here you have Q bars and lepton bars. And so you would end up with a Q bar here. You have interactions like this, where, say, you can have a quark going along and emitting an X particle and turning into a lepton. So, you know, say this is an up quark turning into a positron, let's say, and this would carry some charge. Well, that means a proton can decay, right? You know, if these particles are out there, then this SU5 theory predicts proton decay. And if you put in the details of a realistic version of this theory that has the usual standard model parameters for the standard pieces, it predicts that protons have a half-life of about 10 to the 30 years. But we know that they have a half-life of 10 to the 31 to 10 to the 35 years, depending on which experiment you're looking at. So they're ruled out. You know, this theory doesn't work. You've got to try something else, and people try other things. In the late 80s, it was shown, I think Whitney was involved in this calculation too, but other, you know, some Princeton grad students would have been involved, I think, but showed that you can come up with some compactifications of 10-dimensional string theory, which you do expect to have this kind of issue. You do expect to predict proton decay in these unified theories, but with a half-life greater than 10 to the 35 years. So consistent with current measurements of the proton half-life. You know, that's not an upper limit on the string theory predictions of proton lifetime, but it at least shows that it's possible to have proton decay that's within experimental limits within string theory. So there are a few things like that people can do. Let's see, there are a couple more things with string theory that are of actually considerable importance, even if string theory is not. One is this idea of, well, this probably is important mostly for string theory, this idea of dualities. It turns out that there are, for topological reasons that I wanted to try to summarize for you, but nah, it's complicated. But there are 5 of these things and a 6th, supergravity theory. And it turns out that if you take a certain pair of these, and I think there are 2 or 3 pairs that do this, but say one certain pair of these string theories, these are superstring theories now, you do a perturbative expansion of one of them. If you expand the other one in, let's see, no, you do a perturbative expansion, but now suppose you do a perturbative expansion of that string theory in the inverse parameter. So what was small is now large. It turns out you're looking at this other string theory. So they actually are in some sense the same, you know, perturbations of the same theory with a different expansion parameter. And so people have gone to 11-dimensional string theories that add an extra dimension where you can, you know, have this transformation. It's perhaps a patchwork thing that allows you to do it. There's another kind of symmetry. This involves a compactification on a circle. If you compactify one of the dimensions, the 10 dimensions of string on a circle, the momenta are quantized. So you have this integer tower of possible momenta. But you also have a period of the circle. So, you know, the string could wrap around that n times. And if you interchange the momentum quantum numbers and the winding number of the string, it takes you to one of the other string theories. These are called S and T duality. There are things called double field theories where you double the dimension to 20 and you make these dualities manifest. But now you've got this huge theory. So, you know, people work with that. But if you look at the whole set of dualities, you have these 6 theories. One's a supergravity theory, a maximal supergravity theory. The other 5 are 10-dimensional string theories. there exists a chain of these transformations that connects every one of them. And so the proposal is that, imagine some kind of a two-dimensional sheet of theories with these things around the edge, and somehow they're connected by transformations that take you to another part of that surface. Theories that do or attempt to do that are called M theories, where there's no consensus on what M stands for. It's now just the name of the theory. Mom would be good. The mother of all theories. It's sometimes thought matrix, or there are a few other interpretations for what M theory might stand for. But
heard membrane theory.
Yeah, membrane. Yeah, that two-dimensional thing. Yes, exactly. Membrane theory. Yeah, that makes sense. And there's work that's done on that. So these dualities between different string theories is a new phenomenon. This is not something that we've really run into before, where you get two theories for the price of one. Another advance in string theory, there are a lot of people working on this now, is the ADS-CFT conjecture. What is shown for certain models, I think in 4 dimensions this works, is that there is a one-to-one relationship between gravity solutions and a conformal field theory on the boundary of the space. And that conformal field theory, could be, it could be SU3, something like that. It could be a standard model symmetry, but it turns out that that can be equivalent in some way to a gravity theory. People are taking solutions in gravity, doing transformations that project to the boundary, and you'll hear this called holography, where the theory lies on the boundary of space-time, or the boundary of some space, and all the information about some dynamical theory in the space-time is actually contained in a projection to the boundary. We have that inside any conformal theory. You can project to an infinite boundary and probably retain the interesting things of the theory, but that's a potentially very important development, that we can relate solutions in gravity to solutions in conformal gauge theories. So there's a lot of work being done on that. I think I think Oscar works on that sort of thing. If that strikes your fancy, go talk to Oscar for sure. There's something else I wanted to. I'm rambling. Anybody have questions? Or too many questions? Probably too many questions, right? I mean, physics is huge. You've got to specialize. You're starting on dissertations, right? You're going to look at like one problem, and
I actually had a question.
Yeah. Please.
I was wondering. I kind of had two. So one of them was like, so we got this quantum gravity theory that's a string theory now.
Yeah. Right.
How? And I'm trying to think, like, what's the limiting case where I have to start thinking about it, right? Like, if I got a hot gas and then I cool it down, I have to start thinking in quantum terms. What would be something similar in this case?
Okay. One hope with these theories is that the string corrections to general relativity might, this was an early conjecture a long time ago, might remove the singularity at the center of a black hole. And this was actually my dissertation, to do the black hole solution with the quadratic string terms included. And what it does is it changes the strength of that singularity a little bit and shifts the horizon a little bit, but like parts in 10 to the 60th or something. It's a very tiny effect. So it doesn't magically resolve the dilemma of the singularity at the center of a black hole, but qualitatively it does. Because if you have a hot gas of string, let's see, what is it? The entropy drives it towards a single string. And I'm not sure how that occurs. I haven't worked through the math of that, but this is what I hear. But okay, now you're a collapsing star. You're on your way to being a black hole. Okay, you get towards the center, way inside the event horizon. You're this big, and you've got 1 million times the mass of the sun. Right now, what happens? What happens is at extremely high energy, space-time is no longer compactified, and you're back in 10 dimensions, and you're a single string moving in 10 dimensions. So you at least have a conceptual problem that could be resolved by string theory in that sense, that you would be solving a very different problem when you get close enough to the center of a black hole. That's one possible resolution of the black hole singularity, that you're at such high energy that you're looking at a very different theory. We actually know from the standard model that we have what are called running coupling constants. You remember we put in some momentum cutoffs in order to make some integrals converge when we were doing some scattering things. And those cutoffs, well, you can write some predictions that are independent of the cutoff, and you go measure those things. But there are some results that depend on where you put that cutoff, which means that, right, if it's a momentum cutoff, it actually makes your coupling constants depend on the momentum. And you get what are called running coupling constants for the electroweak and the strong interactions, and or the electromagnetic part and the weak part and the strong part, they actually converge at high energy. So even in experimental particle physics, you see that the coupling constants of the standard model interactions are forming into one thing. If you look at the Higgs mechanism, right, at high energy, all the masses go away. There seems to be, and this struck me as I was writing up these notes, that there is no such thing as mass in any of our fundamental theories. The general relativity doesn't have a mass. If it's asymptotically flat and you have a conservation law, and you can put a large distance Newtonian orbit, and say, oh, the mass of that orbit is the mass we assign to the black hole. That's consistent, and it's the M that's sitting in the Schwarzschild solution. That's good, but it's not necessarily there. Maybe space-time is not asymptotically flat. I mean, we don't see any end to the matter as we look out further and further. What makes us think it's asymptotically flat? It's a good approximation. You get far away from the sun, and space-time is really pretty flat, and so you can assign a mass to the sun, but that's an approximation. In the standard model, all masses come from the Higgs particle. And as the Higgs particle, all right, you've got this Mexican hat potential, right? And at high energy, the Higgs is well above any of the extreme points of that potential. The Higgs is just some field floating around, and using the minimum of that potential as to give masses to WZ, nothing's got mass anymore. That's a meaningless exercise at sufficiently high energy. Now, it's got to be really high, but there are places where we expect to see really high energies. So at those places, you're talking about a different theory, right? It doesn't look like our low energy model that works so well at energies we can produce. There are energies out there that we can't produce. And, don't jump into a black hole to measure them, but you might do some calculations that involve those, and wonder what happens, wonder what happens to the gravitational singularity when none of those particles have mass and all of the interactions are somehow unified with a single coupling constant. So, yeah, things like that. So, how much can we answer from string theory? Not a lot yet, but it's if you look at Einstein's early papers, one of the things that Einstein did was to take seriously the idea of atoms. You know, it runs through his 5 great papers in 1905. You know, one of the things he was doing was thinking about the world in terms of atoms. And that gave him new insights. Well, now it's all quarks and strings and, you know, other stuff. But, you know, there are people now who are thinking about the world in terms of stringy bits. And by thinking in those terms, seriously, you know, okay, the world really is made up of these strings moving around in some dimension. Well, then what does that resolve? What does that say about the Big Bang? You know, the Big Bang is another place where you've got extraordinary energies. So, you know, it was stringy. When was it stringy? Well, you know, shortly after Kaboom. But, you know, at some point, our data gives us no reason to think that you wouldn't see unifying energies at some point in the Big Bang. You know, what you're safe in saying is that, you know, well, you know, when the energy or the science gets, you know, down to these scales, we don't know. We don't have any data for what happens. But lots of people are happy to muse about it. So, so there, you know, some things that might gain insight by thinking of them in terms of string. Any other questions? You know,
I have another one if no one else does.
Yeah, sure. We got that. Kevin, do you need to go at 4? Or yeah, okay.
Thereabouts, yeah.
Yeah, I'm happy to wind it up around 4. But yeah, let's take another question. What you got, Josh?
So the other one that I was wondering about, and I might totally butcher this since I don't know as much about the quantization as all of you do, but I was thinking.
I'll read my book, Josh. I just said.
I know, I'd love to.
Yeah.
So for these, I know for spinors that there are topological constraints on just even their existence either locally and globally, and I don't remember which one of those ones it is.
Yeah.
But the question I was going to ask you was like, so I have this string now, and if I think about this string as a spinor, which maybe is a horrible idea, I'm wondering like if there are any topological constraints on this string kind of space and what that would mean for like space-time, you know, because I'm interested in, you know, a kind of GR question. And I'm like, well, if I have a nice topological constraint from the actual theory and the really high energy regime, maybe it will constrain down the solutions I can have physically more in what I'm working on. That was a lot there.
Yeah, well, one word answer, probably. Yeah, there are probably your topological issues you have to deal with when you're dealing with string. In fact, the compactifications, the way that, say, Witten got this result, or that, you know, Lara is looking at Calabi-Yau compactifications, is on the effect those topological shapes have on the resulting 4-dimensional theory, which we actually know very well at low energy. So there has to be parity violation. That's not easy to achieve with string compactification. You know, you have to be able to do that. That's some kind of topological constraint. So not any string compactification will do. So yeah, these considerations are important. What you're saying about spinors, I'm not sure how that plays out in the supersymmetric theory, right? Yeah, you have spinors, and spinors seem to all know about one another because of the exclusion principle. You know, if all the spinors in the universe except this one are in, you know, such and such a state, you know, this one, you know, can't be in one of those states, right? It's it somehow knows, right? So yeah, there are topological considerations. I don't know how that really plays out even for spinners. Certainly not for a. Did you have a question, Kevin?
No, I was waving at somebody in the background. Sorry.
Oh, okay. Yeah, these spinners. Yeah, if you're dealing with a supersymmetric theory, you've got all these spins, you know, coupled to bosonic fields, and I have no idea what the exclusion principle is going to say about that. You know,
I was more thinking for like the space time. I know you need, this is going to sound obvious and silly, but you need to have an orientable space-time manifold. And then there was that, like, you know, these, I'm thinking the Stifle-Whitney classes. Like, I know that it needs to be orientable, and then the second one guarantees you can have spinners. And if you don't have that, it's...
That's right,
And I'm trying to extrapolate that to this situation.
That's certainly true. So, yeah, you need to have spinners, you need to have parity violation of part of the interaction, so on and so forth. And looking at a particular compactification string, you may or may not have those properties. So you may be able to rule out a million different compactifications because of that. Yes, those classes are a good guideline. If you can come up with any more topological classes, you know, it'll have your name on it, right? Those are not easy to come up with, and they're important. They're a good way of classifying spacetimes. Yeah, I want to share with you something I just stumbled into in my last paper with Davis. We were looking at sources in biconformal gravity, which you all know is, you know, by working, and we came up with some, and you know what you have to do with the action to make them consistent and so on. But as a sort of preamble to that, I started looking at what you do in other conformal gravity theories, in particular in Veil gravity, which has a fourth order conjunction. I proposed some new sources for those, but the thing that's interesting is that, right, those have full conformal symmetry, which means, right, the special conformal transformations, they're really translations of a point at infinity, and in order to have that consistent, you have a topological constraint. The space needs to be flat to the initial space where you define the conformal group needs to be compact. Needs to be compact to have inversions. Well, what if our world is? You know, it could be. And so I looked at probably the static spherically symmetric solution in Veil gravity, and was wondering, well, you know, what happens if you have inversion symmetry? So in addition to the usual 1 over R thing, you've got something that grows linearly in R. That solution is actually inversion symmetric. So I put in some numbers, and it turns out that, you know, in order for, you know, the constant with the linear term has to be really small in order for it to be consistent. Well, if you take the inversion radius, so you're going to invert everything through some sphere. Inside goes out, outside goes in, and that sphere has some radius. So if you take that radius to be on the order of the known universe, then that parameter turns out to be just about the right kind of small. So you could build an inversion symmetric cosmological model if you want. And yes, it's got topological consequences, but it can be made consistent. Yeah, theories with inversion symmetry, whew, you know, what do those look like? You know, the world's really big, you know, bigger than a lot of people like to admit. You know, I like to think of our knowledge as a bright luminous sphere in an infinite black space, and that sphere is growing. It's still always an infinite black space out there, that there is more yet to know than we will ever know, even though, we are constantly learning, our knowledge is constantly spreading. I think my take on things, there are always going to be interesting mysteries. So your sound's off, Kevin, but I think that's probably a good place to call a halt. I will, maybe I'll just email you all copies of the PDF when I finish writing up the string stuff. It's a bare bones introduction, but I want to work out at least up to the Poincare, the algebra. So when I get there, I'll send you these copies. If I can, I'll clean this up and I'll post it online as well. It may be a little bit because I've got to do a few other things first, but anyway, thank you all for sticking with this for these many months. This has been a lot of fun. The summer's been a little bit crazy. I wish I could have interacted more with each of you. But in any case, the content is online. The recordings are there. The book is there. So enjoy it. And I'm sure I'll see you all soon in one context or another.
I wanted to thank you for sending out that email to me with the book. So
I knew you'd be interested. You're welcome.
And are we meeting in a week? Sorry.
No, I think this is as far as we'll go with this. So let's call this the end. Now I did want to, some of you may sign up for Quantum Field Theory 2 in the spring, and you're able to, as a way of filtering that, do the exercises. The book has, they're mostly easy. If any of them turn out to be hard, just email me and we'll figure out what to do about it. I don't mean to make it hard, but I just want to see that you have looked at these things in more than passing detail and thought about the issues. So in order to get credit for the course in the fall, that's all I'm going to ask. That no final exam unless I ask you to do the open string boundary condition. No, I'll make it easy. Just do the exercises, and you'll get credit for, what is it? 6940, I guess is the number. But anyway, thanks for your attention.
Thanks a lot.
See you later. Thank you.
It was a fun time, at least for the parts I was here for. I'll catch up on everything and be good to go. So.
Okay. Anytime any of you have questions, just email me, text me, whatever. Happy to chat about any of these things anytime. It's physics. It's fun. Okay.
See you later.
I'd better run, but I'll see you all later.
See you later.
Bye.
Catch you later.